This is the Thermo Scientific SPRD GN kit. And this is a technical difficulty. The SPRD GN is a compact, spectroscopic gamma and neutron detector. Here we have the device itself, a pouch for the belt, spare batteries, the lutetium test adapter, a USB to IR cable, the docking station, and this cutout is for optional equipment. As you can see, the device is rather small, 4 buttons on the front side and 1 on the top. The alarm indication lamp is visible from 2 sides, and this is the speaker. And the headphone jack. The IR window is on the bottom side. And the scintillation crystal with a plus sign showing the preferred measurement direction. The test adapter is made from 36 grams of lutetium oxide, which is not legally considered a radioactive source. It can be used for test and calibration purposes. Lutetium-176 is a beta- emitter with prominent gamma peaks at 88, 202 and 307 keV. Half-life is around 3.8 times 10 to the power of 10 years, so it probably will still be radioactive tomorrow. The belt pouch is made by a gun holster company called DeSantis. Here we have the PC connection via IR port and the docking station where the cable is mounted. Software and handbook are provided on a USB stick. This is how you connect the device to the PC, where you can export gamma spectrums and change hundreds of different settings. The protective rubber sleeve can easily be removed. Since the SPRD GN is water resistant according to the IP65 rating, the headphone jack is sealed. The battery compartment is also very well sealed. Quick size comparison. The SPRD is even smaller than the already compact Radioscan 701A. The heart of this spectroscopic radiation detector is a 12.5 by 12.5 by 30 mm large click scintillator, which is an advanced and rather new type of combined gamma and neutron detector, coupled with a silicon photomultiplier. CLIC is short for cesium, lithium, yttrium chloride, which is doped with cerium. You cannot directly compare this scintillator to the cesium iodide crystals on the table, but my drawing gives you an idea of the size and volume of this detector. The interaction of neutrons with lithium-6 causes a sharp peak at 3.3 MeV, which can be discriminated from gamma rays by the software. The detector resolution FWHM at 662 keV is around 7% according to Thermo Scientific. My device manages to achieve a much better result or 5.3% according to the test protocol. Pressing the lower button for 2 seconds turns the device on. Holding the button for a longer period keeps the start screen from disappearing. Learning means that the device checks the background radiation. Pressing any button one time unlocks the keyboard and turns the backlight on. Pressing the right or upper right button 2 times turns the speaker on. In this case, no click divider is configured, which can be done in the software. Pressing the lower button, neutron count rate, gamma and neutron count rate, search mode with horizontal line for the next alarm level, and back to the home screen. Pressing the upper button, gamma dose rate, gamma dose, peak and mean gamma count rate, peak and mean neutron count rate. Holding the upper button for 3 seconds switches the device to the Nuclide ID. And back to the rate meter mode. Measuring units for neutrons, counts per second or counts per minute. And for gamma radiation, levels, grays per hour, REMS per hour, Röntgens per hour, sieverts per hour, and counts per second or counts per minute. In dose rate mode, you can display peak and mean dose rate, for example in microsieverts per hour, and also combined gamma dose rate and neutron count rate. Operation modes include the rate meter mode, scalar mode and Nuclide ID mode. If we attach the lutetium adapter to the backside, we trigger the alarm and start an automatic Nuclide ID. To use the adapter for calibration purposes, we first have to start the lutetium adjust in the menu. I have set the Nuclide ID time to automatic with a limit of 10 minutes, which is fine for field use. The identification is completed and now we can take a look at all the details. So, lutetium-176, industrial, 100% confidence. The live spectrum view. The identified peaks with the reference energy. Energy error referring to the reference peaks. The channel number. Total counts per peak. Relative signal. Peak width. And the spectrum is automatically saved. Now we try to identify a mystery source in a lead container. Wall thickness is 10 mm in all directions, and for extra difficulty we add 20 additional millimeters of lead. Switching to the nuclide ID mode. Pressing the up button starts our spectrum. The preferred count rate for nuclide ID with this device is between 75 and 5000 counts per second. If you leave this count rate range, it says move closer or move back. So, the ID is done, radium-226, naturally occurring radioactive material, 70% confidence, not bad. The source in question was uranium ore, which is easily identified by the radium gamma peaks, even through 30 mm of lead. Let's test another source, this time something that the device can't identify, because the nuclide is not listed in the library. Let's see what will happen. We get 2 alarms, one for reaching the 50 counts per second limit I set, and one for an artificial source. The nuclide ID was started automatically. Okay, we are done. Sodium-22. And I can tell you this is definitely not sodium-22. But it's a very good guess, I think. A sharp peak at around 500 keV. Reference is 511 keV. Seems plausible, but the nuclide in question is actually the beta- emitter Krypton-85 with a gamma peak at 514 keV. Sodium-22, on the other hand, is a positron emitter causing an annihilation peak at 511 keV. As you can see, this source is rather weak. Only 0.4% of all decays result in a 514 keV photon being emitted. Okay, let's try some food testing with the scalar and also with the nuclide ID. For this purpose I use some lead bricks with 20 mm thickness. More convenient than setting up my larger lead castle. First we try the scalar mode. 10 seconds of countdown. Let's see what the background count rate will look like. Measuring time is set at 500 seconds. So, 3.2 counts per second. Time for some dried mushrooms. 4.1 counts per second. Looks like our food is contaminated, but this could be harmless potassium-40. To be sure, we have to record a gamma spectrum, this time with a preset time of 3600 seconds, which is not a whole lot of time for a small scintillator and a very weak source. I haven't tested this beforehand, so I'm kinda curious. One hour has passed and the automatic nuclide ID works like a charm. Cesium-137, industrial, 80% confidence. A tiny 662 keV peak. With only 12 total counts. And a total count rate of 4 counts per second. Really impressive. Now we have one last thing to do, testing the sensitivity to neutrons. If you own some spicy uraninite, you are also in possession of a neutron source. Due to spontaneous fission, uranium-238 is emitting roughly 0.014 neutrons per gram and second. In this example I use some high-grade uranium ore and paraffin wax as a neutron reflector and moderator. The alarm threshold is set at 0.3 counts per second, which is quite a high count rate considering the neutron background on this table is at 0.009 counts per second. And here it is, the distinctive neutron alarm, obviously combined with the alarm for gamma radiation. As you can see, we can reproduce the neutron alarm again. Awesome. I'm not really a fan of endlessly rattling down all the technical specifications, so here's a list that you can read if you pause the video. Conclusion. This compact device offers an insane amount of flexibility. It is a dose rate meter, radiation pager, neutron detector, gamma spectrometer, radioisotope identification device, all combined in one tiny unit that fits in your pocket. As you would expect, this comes at a price. In fact, the price of a used car. Well, that's not completely correct. After some further investigation, you could actually buy a new Dacia Sandero for less money than Thermo Scientific charges for this device, at least in the UK. Since Thermo is a US company, it probably is quite a bit cheaper in the US of A, even though the device is manufactured in Erlangen, Germany. In my opinion, the SPRD-GN is a good example how the times have changed. It is still better than all comparable consumer devices on the market. But wait, there are comparable consumer devices? What a time to be alive. This goes to show how far talented people have pushed the boundaries. I'm thinking of small companies like Radiacode, or talented individuals like Alex, the developer of the RACIT. You still can't get 100% of the capabilities of the SPRD-GN anywhere else, but consumer devices are closing the gap, at a fraction of the price. Just 10 years ago this was unthinkable, where all you could buy was a Gamma Scout or some surplus army counter the size of your head.